Good morning, ladies and gentlemen. I would like to invite all the guests and participants to be seated as our opening ceremony will begin shortly. Just please make sure that your handphones are on silent mode or turn off. Thank you. A very good morning to Professor Dr. Hidetoshi Sekiguchi, Chairman of Liaison of ASEAN, the Society of Chemical Engineers Japan. Professor Dato Dr. Engineer Wan Ramli Wan Daud, the Professor of Chemical Engineering, Faculty of Engineering and Built Environment, University Kebangsaan Malaysia. Professor Dr. Mushtaq Al-Atabi, Dean, School of Engineering, Taylor's University, Malaysia. Keynote speakers, Secretariat of SOMCHI and RSCE 2014, participants, lecturers, and students. Welcome to the 27th Symposium of Malaysian Chemical Engineers, SOMCHI 2014, and 21st Regional Symposium of Chemical Engineering, RSCE 2014. My name is Ismail MJ, a lecturer in School of Engineering, Taylor's University, and I will be your MC for today. Ladies and gentlemen, on February 15, 2008, the US National Academy of Engineering, NAE, has announced the grand challenges for engineering in the 21st century. A diverse committee of experts from around the world convened at the request of NAE, revealed 14 challenges that, if met, would improve the way we live. Make solar energy affordable, manage the nitrogen cycle, provide access to clean water, engineer better medicine, just to name a few, are some of the challenges that is closely related to chemical engineering and, of course, demanded for great involvement of chemical engineers. For this year Dual Force Symposium, Taylor's University, as the host, is proud to gather all the great minds of academicians, practicing engineers, and researchers in this two-day event to address some of these challenges. I heard we have a big delegation from Indonesia. Where are you from Indonesia? We also have a delegation from Japan, the Philippines, India, okay, Thailand, Poland, and not to forget, from our home country, Malaysia. With the theme of addressing the grand challenges of chemical engineers in the 21st century, SOMCHI and RSCE 2014 could be one of the best platforms for us, the chemical engineers and the engineering community as a whole, to gain some understanding and knowledge on what have been done by the practitioners and researchers from all over the world to tackle these grand challenges. This year's symposium, in total, we have 3 plenary sessions, 9 keynote sessions, and 168 research paper presentations. For the plenary and keynote session, we are very blessed and fortunate to have 12 prominent figures from the international, academic, and industrial world to share some of their insight with us. We have on board, let me introduce, again, Professor Dr. Hidetoshi Sekiguchi from Tokyo Institute of Technology, Japan. Prof, maybe you could just stand up and wave your hand. Okay, thank you. We also have Professor Dato Dr. Engineer Wan Ramli Wan Daud from University Kebangsaan Malaysia. Professor Dr. Mushtaq Al-Atabi, Dean, Taylor's University, Malaysia. Associate Professor Dr. Adam Figil from Wrocław University of Environmental and Life Sciences, Poland. Mr. Hans Tan from Schneider Electric, Malaysia. Associate Professor Dr. Edwin Chung. Dr. Edwin? Okay, Dr. Edwin Chung from Taylor's University, Malaysia. Professor Datuk Dr. Engineer Abdul Wahab Muhammad from University Kebangsaan, Malaysia. Professor Engineer Dr. Abdul Aziz Abdul Rahman from University Malaya, Malaysia. Dr. Christina Pang from Environmental Resources Management, Malaysia. Professor Dr. Piyasan Prasadam from Chulalongkorn University, Thailand. Professor Dr. Muhammad Ali Hashim from University Malaya, Malaysia. And last but not least, Professor Dr. Susan Gallardo from De La Salle University, Philippines. So, to all the participants, please take note, some of the sessions are going to be held concurrently. You may refer to the program booklet to pick the perfect combination of sessions that will best suit to your interests and your needs. Okay, enough with the introduction. Let's move on to our next agenda. Ladies and gentlemen, now I would like to invite the most hardworking person behind this event, Dr. Chong Chen Hua, Associate Dean, Learning and Quality, School of Engineering, Taylor's University, come the Chairman of SOMCHI and RSCE 2014 to give the welcome speech.
Thank you, Ismail and Jay, for the introductions. A very good morning to the Honorary Chairman, Professor Engineer Dr. Datuk Wan Ramli Wan Daud, and Professor Dr. Mushtaq Al-Atabi, and guest of honor, Professor Hidoteshi Segikuchi. Invited keynote speakers, colleagues, ladies and gentlemen, welcome to Taylor's University. So it is a great honor for me to host and distinguished guests from 54 different institutions. I would like to thank to the organizing committee for all the efforts in organizing this event. I'm sure that this will be a very fantastic event for together all the engineers from this region. Most importantly, I want to extend a warm welcome to all of you on behalf of Taylor's University. Taylor's University realizes its significant responsibility to the community and society in addressing the demands of the 21st century global evolution. Taylor University, with a great pleasure, is proud to gather the great minds of academicians, practicing engineers, and students especially from the Asia region together in this international symposium to address the grand challenges of chemical engineers in the 21st century. The theme for this symposium is addressing the grand challenges of chemical engineers in the 21st century. Chemical and process engineering are the forefront tackling of many of the world's tough challenges. Institution of Chemical Engineers, ICHEME, identified 4 key challenges which chemical engineers have a prominent role to play in this century. They are energy, food and nutrition, health and well-being, and water. The American National Academy for Engineering, NAE, on the other hand, also identified 40 grand challenges of human race in the 21st century, the majority of which require the great involvement of chemical engineers, means all of you, to be there to share some ideas how to address the grand challenges. So I'm here. I would hope that you can enjoy the time here, and I will end it with a short virtual tour to show you Taylor University campus. Thank you.
Thank you very much, Dr. Chong. To echo what Dr. Chong said just now, welcome everyone to Taylor's. You have just visited almost all part of Taylor's by watching the video just now. Okay, next, I would like to invite Professor Dr. Mushtaq Al-Atabi, Dean, School of Engineering, Taylor's University, to give his opening speech.
very much. Chi Chong told me that they are not he won't be saying anything, and the MC won't be saying anything. So I just copied something from the website, and they said everything I'm going to say. So I'm going to try to make it sound different, actually. So let me see whether I can do this or not. Honorary Chairman, Professor Insignor Dato Wan Ramli Wan Daud, Guest of Honor, Professor Hidetoshi Sekiguchi, Delegates of SUMCHE 2014 and RSE 2014, distinguished guest sponsors, keynote speakers, dear colleagues and students. To our international guests, I wish to bid you a welcome to Malaysia, and to our national colleagues and everyone else, I would like to welcome you to Taylor's University. In a recent report produced by the Institution of Chemical Engineers, ICHEME, reviewing the institution's technical strategy, concluded that chemical and process engineers will be at the forefront of tackling many of the world's tough challenges. And I think you will be hearing this word, challenges, great challenges, grand challenges, global challenges, again and again throughout this conference. As a matter of fact, this is one of the techniques that we use it to brainwash our students, to show them how important engineering is. So this is the word that they hear from my welcome note to them when they first come in until they graduate. And we believe that when we frame the tough issues, the tough existential issues that we are facing today, collectively, as a human race, as a challenge rather than an issue, this will put us in a better frame of mind to enable us as engineers to try to convert these challenges and transform them into opportunities and unlock the opportunities inherent into them. Against this background, the 27th Symposium of Malaysian Chemical Engineers and the 21st Regional Symposium on Chemical Engineering confer at Taylor's to discuss, exchange opinions, and network. Taylor's University realizes its responsibility to the community and the society at large to address the grand challenges for engineering and grand challenges for our existence collectively. And that's why we are the first and only university outside North America that has an active Grand Challenge Scholar program that is recognized by the National Academy of Engineering in the United States. We have taken the challenge to educate engineers who are first aware of the grand challenges to our existence, and secondly, they are working systematically towards addressing these challenges. Now, today with us are colleagues from Bangladesh, India, Indonesia, Iran, Iraq, Japan, Jordan, Kazakhstan, Pakistan, Philippines, Poland, Thailand, and also Malaysia. And this is really a testament for the fact that the challenges that we are facing are global in nature, and they can be addressed only through a coordinated and global effort. I'm confident that this conference will represent an important milestone on our way to collectively address these grand challenges. Before I end, I would like to again thank all the delegates and welcome them, the keynote speakers, and also the organizing committee of this conference. Our sincere gratitude also goes to our sponsors, mainly the Society of Chemical Engineers, Japan, and the Institution of Engineers, Malaysia. I would like to wish you a very fruitful conference, and as we say at the School of Engineering, always dream big, be different, and have fun. With this, I would like to announce that the conference is open, and I think they have a video to show you right after this. Thank you very much.
Thank you very much, Prof. And thank you to the person who have provided us the video. Okay, ladies and gentlemen, we have now come to the end of today's opening ceremony. Professor Sekiguchi will shortly deliver the first plenary speech entitled Extensive Potential of Plasma Technology for Chemical Processing. But before that, I want to take just a few moments to thank our sponsors of this event, the Society of Chemical Engineers Japan and the Institution of Engineers Malaysia. I have an announcement to make. To all our SCE International Advisory Committee, you are invited to attend a meeting at TTIC meeting room at 1 p.m. today. And we have a special photography session. You just have to remain seated and pose the biggest smile to our cameraman. Where's our cameraman? Yes, yeah. Make sure you smile. All right. On behalf of SOMCHI 2014 Secretariat and Chalmers University, I hope you will have wonderful time here. To the next plenary session chairman, Associate Professor Dr. Nurius Miza and Dr. Veena Doshi, over to you. Thank you.
Assalamualaikum and good morning, everyone. Today we have three plenary speakers with us, Professor Hidetoshi Sekiguchi, Professor Mushtaq Al-Atabi, and also Professor Dato Engineer Dr. Wan Ramli. Professor Hidetoshi's research interest is on development of innovative reaction process for energy and environment issues using external energetic fields such as plasma, ultrasound, supercritical fluids, and so on. Okay, without further ado, let me welcome Professor Hidetoshi Sekiguchi. You have 25 minutes. Thank you.
Good morning, ladies and gentlemen. Thank you very much for the kind introduction, and also thank you very much for giving me an opportunity to present here. It is great honor for me to present my talk concerning my research topics. So the time is limited. We can start. Let's start my presentation. Okay, so today's topic is about extensive potential of the plasma technology for the chemical processing. Okay, so maybe you know plasma very common. So sometimes we say refer to the fourth state. So the matter of the sequence of solid, liquid, gas, and plasma. So when we add the energy to the material, so the melting, the gasification, and finally the ionized, we can get the plasma like this. So of course the plasma has the containing of the electrons, ions, sometimes the neutral particles, and some particles is the excited state. So the plasma is eliminated. So just the emission of the UV or the visible light. And we can this is a definition that the plasma is must be the electrical neutral. This is the definition of the plasma. Okay, so we can see the plasma in the around the world also. So you can see the plasma containing in the sun, the lightning. Sorry, this is Japanese. So the aurora and also the candle also we have the plasma inside, and as well the spark. And usually plasma can be obtained by the electrical discharge. So this is a very common. So you can see the fluorescent is a very common plasma the technology the inside in the fluorescent. So artificially we can generate the plasma using the electrical discharge. Okay, so when we define the plasma, one is a big important property is the Debye length. So the Debye length is just the definition of the plasma of the size of the plasma, and we can see that this Debye length we can see the two important parameters. One is the electron temperature. Of course, the plasma contains electron, so that we notice the electron temperature, and also this one is N0 means electron density. So these two properties are very important to define the plasma. And this is the plot of the relation between the electron density and the electron temperature from this literature. So for example, high electron density and high electron temperature, so we can guess this one is just a fusion plasma. So the very, very high energy, so this is a fusion plasma area. And also this is a fluorescent light, so relatively low electron density, however, the relatively high electron temperature. So we can see the plasma, we can understand the plasma can be categorized using the electron density and the electron temperature. So this table shows the plasma categorization. So usually we classified into the two big classification. One is the thermal plasma, and another one is non-thermal plasma. It means the equilibrium or the non-equilibrium. So this means, so please notice this temperature. So usually the equilibrium plasma or the thermal plasma is almost the same temperature of the electron and the gases. So it means the neutral spaces, ion spaces, and the electron is the same temperature. However, non-thermal plasma, only the electron temperature is very high. However, the gas temperature is very low. So that's why fluorescent exists without melting the glass. However, if we generate thermal plasma in the fluorescent, it is easy to melt. So anyway, so we have the two categorization, the big categorization. And also we can notice that the pressure, the generating in the plasma. For example, so thermal plasma is usually generated under the atmospheric pressure. And also the non-thermal plasma, conventionally, it is easy to obtain this plasma under the reduced pressure. However, the recent technique, we have the technique to generate the non-thermal plasma easily using this discharge. So I will explain later about this discharge. Considering the chemical processing, I believe the atmospheric pressure is very convenient for using the plasma. So I think the technique is very suitable for the chemical processing. Next, please. Okay, first I would like to explain about the thermal plasma. And so we have the two generating methods to get the thermal plasma using DC arc discharge and the RF radio frequency discharge. Next, please. Okay, I'm sorry that this is a relatively busy slide. However, as I said before, so the thermal plasma has a high temperature, or also the near equilibrium state, and so that this plasma provides rapid heating, and also when we use the working gas as hydrogen, we can get the reductive circumstances, and then we can we use the oxygen, for example, the oxidative circumstance we can get. So this thermal plasma provides the high temperature processing, for example, material processing to make the particles, films, syngas process, syngas production, etc. And the environmental processing is mainly the waste treatment, just the destruction and the vitrification. And this field is very conventional. So many already we have the many commercial processes, the welding, cutting, refining the furnace. That's very famous process using the summer plasma, and also the surface treatment like this one, spray coating something. Now that I'm talking about both first two fields concerning using the summer plasma. Next, please. Okay, so this is the generation technique to get the summer plasma. One is the DC arc discharge. So when we apply the cathode to anode the DC voltage, so we can get the plasma like this one. And when we flow the gases between the two electrodes, we can get the plasma like this one. So we say that this is the plasma jet. And this type is non-transfer type. And the other case is the anode is the bottom side. So this case, the discharge take place between the two electrodes. This is cathode, this is anode. So in this case, the energy from the discharge is the most of the energy to transfer to the anode. So we can treat it material as an anode. And another type is the RF discharge. When we apply the radio frequency voltage to the coil, like this one, so we can get the plasma here. So the relatively big plasma can be obtained compared to the DC arc discharge. Next, please. So just this video about the DC arc the plasma jet. Click. So this is like this one, so just we can get the plasma like this. Okay, next please. Okay, so this is the advantage and disadvantage of the both two methods. For the DC arc discharge, as I explained, this system has a electrode, so the working gas is contaminated as the electrode material, and also the working gas limitation. For example, when we use the oxygen, the electrode is easy consumed. And however, this power system is very cheap and compact, and also easy to scale up. However, the RF discharge, so this discharge has no electrode, so we can use various gases, so hydrogen, oxygen, nitrogen, so any gases we can use, and so without contamination, and relatively large volume, and so the low gas velocity, so this is suitable for the material processing. However, these are the disadvantage for the RF discharge system. Okay, the last 20 years, the summer plasma application, many application is the main application is focused on the particle formation, especially for nanoparticles. So just could you click the again? So just plasma introduce some precursors, solid, liquid, and vapor, and then plasma decompose the precursors. Please click the. So just the radical ion vapors exist in the plasma, and then flick like the product like this one, and so we can get the plasma like this. Particles, nanoparticles here. Okay. Okay. Next, please. So this is one example of the nanoparticle formation using the summer plasma. So when we introduce the aluminum powder to the summer plasma, and with some oxidative circumstances, so we can get the aluminum nanopowder easily, like this one. And next, please. And this case is the aluminum doped titania. So when we introduce that titanium metal, and with as well as aluminum, so we can get like this the doped material. Also, when we use the methane as a working gas, we can get the TIC easily, like this one. Okay. And also the last type is the plasma jet type, and this type is just last type, the non-transfer type. And this type of transferred arc system. So when we put the aluminum, the metal here, and when we discharge between the two electrodes, so this is a transfer type. Also, this type that we can get aluminum nitride easily using the plasma system. Okay, next. So this is a summary of this one. So material processing, the plasma sources do have so many, and when we use the many gases combination between the argon and something gases, so materials reacted in the plasma, and then we can get many materials types like this one. Okay, next please. And another example is a diamond synthesis. So this is also the very famous topic concerning using the thermal plasma. And when we use methane as a working gas to introduce the plasma and irradiate the plasma that's the substrate, we can get the diamond film like this. Next, please. So like this system. So the crystal size is depend on the methane concentration, like this one. And also, next please. So this one is when we change the precursor as a hydrocarbon, acetone, isopropyl alcohol, benzene or toluene. So the morphology changes like this. But anyway, the all film is a multi-crystal diamond film. It is easy to obtain. Next, please. Okay, so the next topic is about environmental processes. So I'm so sorry, this is also the busy slide. However, please understand that the thermal plasma has a high temperature and high activity. So when we consider the material environmental the issues, so one is the plasma pyrolysis, and one is the plasma gasification, and another one is plasma compactation. So just the waste is treated as a pyrolysis or the gasify or the vitrificate to compact it and combination. So the target material is, for example, the PCB containing oils. That means the hazardous liquids, the CFCs, PFCs. Also the municipal solid waste. So many waste in the Southeast Asian countries as well as Japan. And the hospital solid waste, this is infected by the material. And also the bottom ash of the fryers, this is containing heavy metals and the contaminated all the sewage, the waste, and also low level radioactive waste. So we need to compact the material. So using this technique, and also the asbestos or something. So this one is also the considered to treat using the high temperature thermal plasma. So this is the commercial or the proposed from the company system. So this is the ash vitrification system. So plasma discharge take place between here and this is the fly ash, and so melt that we can get some of the material here. And also this is the asbestos treatment. So just we introduce the asbestos containing material. This is a plasma torch here, and so the asbestos melted to like this one. Okay, next please. And also this one is the municipal solid gasification. So just we introduce the waste here, and this is a plasma torch. So we can get the synthesis gas here. So containing the CO and the hydrogen. So we can use this one for the another fuel, alternative fuel. And this is just a system. So just the plasma torches here. So this is just a proposal of the US companies like this. Okay. And also the concept of this one is the treatment of the plasma of the CFC. Just the plasma is the decompose this material into the stable, thermally stable, dynamically stable spaces like this one. And then we can treat after using the scrubber or something. So it is completely treat the hazardous waste. Next, please. And the one is the commercial product in the Korea. This is just a very complexity treatment system of PFCs using the thermal plasma like this one. So the just the plasmas here, so like this system. Okay. So the you understand the plasma technology is especially the thermal plasma is using the high temperature. However, from this slide, I would like to explain about the non-thermal plasma. So this is just the many techniques to get the plasma. However, this plasma containing the high temperature electron. However, the low gases at low temperature. So we can utilize this active electron. Okay, next slide. So again I explain about heavy particle temperature. The neutral gas temperature very low compared to the electron. So this plasma electron impact reaction is very important, and as well as the UV emission also and also so this is the temperature is very low. So this is important things. Processing with temperature weak material. So it means this plasma can be applied to the temperature weak material. So just I will explain the example later. And also generally low pressure is required. However, recently we can get this plasma in the atmospheric pressure. And also the radical is very important. So because the high energy electron they produce the high active radical. So the low temperature processing, we have some the application, material processing, environmental processing, and also recently the sterilization and the medical application is very popular. This one. So I will explain that very shortly later. Next. Okay, so this is the technique to generate non-thermal plasma under atmospheric pressure. This is very common. So we attach the electrodes to the dielectric material, and then we apply the high voltage, alternative voltage, so we can get the plasma here. This will say the silent discharge or the dielectric barrier discharge. And this case is the packed bed discharge. So when we put the dielectric material here, a particle here, and then we apply the high voltage, similar to these cases. So we can get the plasma like this one. And this case is also similar to these cases. So this is dielectric material, and then we can get apply the voltage to the two electrodes, so we can get the plasma around the electrode like this. And this is relatively different from these matters. So just we apply the very short pulse, so that we can get the plasma like this one. So just very short pulses, so without no covered with a dielectric material. However, we can get the plasma like this. So both those plasmas are the non-thermal plasma, very low temperature. However, electron temperature is very high. Okay, so this is the dielectric barrier discharge behavior. So please click this one. So just we can see the very small micro discharge take place in these two electrodes. So almost one discharge is less than 100 micron. So each discharge is very active. So when we flow the gases, so we can treat the gases like this one. So anyway, this is the micro discharge. Okay. So using the DVD, one very famous application for the commercial system is the ozonizer. Maybe you know the ozonizer. So when we get the non-thermal plasma, as I said before, the electron temperature is very high. So this reaction occurs, and it means the high electron temperature that provides the dissociation of the oxygen molecule, and then we can get the ozone like this one. So this is the ozonizer, a commercial ozonizer. And in Japan, especially Tokyo, the tap water, drinking water is very safe. This is because tap water is treated by the ozone, this system like this one. So the ozone bubbling is to sterilize the water like this one. So this is just a tap water system. So here we can use the ozone to treat the water like this. So this is the common system in Japan. And this one is a very same configuration, but this is a high voltage electrode. Outside is low electrode covered with a dielectric material. So we can get like this non-thermal plasma jet. So you can see that we can touch the plasma like this one. So this is a low temperature. As you know, you understand that this is a low temperature. However, this plasma the elimination means this plasma contains a high reactive material. So we can apply this one to the chemical processing. Next, please. Okay, so when we change the gases, this is the argon gas, and this is the nitric acid, N2O, and the oxygen, so we can get like this plasma easily. Okay, this is a photo sample. Time? Okay. So anyway, so the time is constrained, so the limited, so okay, it's to be skipped this one. Okay, so just the application of the like this one. So I think it is, may I use the microphone to in the front of the PC? Just okay. Sorry, the time is limited, so just okay, so just we succeed in the epoxidation of the like this one. Okay. And also the animation like this one. And also the hydrogenation of this one. So we can apply the many chemical processing using the plasma jet like this. So this is we can hydrogenate it using the plasma. And also this one is the low temperature. So when we cool down the plasma gases, so we can get the plasma around the -10 degrees Celsius. And this is just an example of the sterilization. And also, this is the microwave discharge. So the different plasma generation system. So we can get many gases as a plasma state. Get air, steam, combination of the water, steam, and the hexane and the CO2 or something like this. So we can use this plasma for the chemical application. And also this one is the air plasma that treated asbestos contained materials and the dehydration of the materials. So okay, this is another technique of the gliding arc discharge. So like this discharge combined with the spouted bed for the particle processing. And then we can get the coating of the plastic materials like this. And the last one is the recent topic in the discharge in the liquid. So we can get the plasma in the liquid. And so this is apply for the purification of the water like this. And this one is an example of the discharge in the supercritical CO2 like this one. So anyway, so time is limited, so we conclude my talk. So plasma generation is the use energy required. So anytime that we need to consider the cost of the generation of the plasma. So when we consider the plasma properties, especially electron temperature, electron gas temperature, electron density, as well as radical density or something, and so we need to consider the plasma process has a high value added product or the high efficiency or the high performance something. So anytime we need to consider this the key point for the get the commercial or the applicable chemical plasma processing. I'm sorry to hurry up my presentation. However, I hope the plasma system in future, many the plasma system is available in my in the world, I think. Thank you very much for the kind presentation.
In the interest of time, I welcome the questions after the last presenters towards the end. Yeah? Chemical engineers, which we all are, most of us actually, except Professor Mustaq probably, we love mathematics and sciences, in particular chemistry. And the previous speaker talked a lot about chemistry, and I hope we move from the basic sciences from chemistry to engineering. The next speaker, without long introduction, we have known Prof. Wan since long back. In fact, he was promoted as a professor before I even graduated. So that's his how senior it is. Yeah? Prof. Wan, he can talk a lot. He can talk on so many topics from accreditation, plant design, and so on. Luckily today, yeah, he's going to talk about fuel cell. Yeah? Hopefully we can find some understanding, we can find some new knowledge regarding fuel cell. One thing about fuel cell is that normally it requires hydrogen, and we don't have hydrogen on Earth. So hopefully Prof. Wan can enlighten us. How are we going to get the fuel for the fuel cell? Prof. Wan, give it to you.
Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. I would like to welcome all the colleagues from all over ASEAN, Prof. Yasan, Prof. Suzanne, Maria, and the rest, as well as colleagues in Malaysia. Welcome to this nice campus. And our host, Prof. Mustaq, is going to talk about something about engineering, education, and so on, and the challenges that we face. So I will be talking about how chemical engineers can contribute to energy, which is one of the grand challenges that Prof. Mustaq has just told us. So in future, we will see not only mechanical and electrical engineers in the energy industry, in the power industry. We will also find chemical engineers working in fuel cell power stations in the future. And of course, as the chairman said, I mean, there is no hydrogen freely available on Earth. We can have hydrogen, a lot of hydrogen in the sun, but it's difficult to get from there. But of course, we can actually produce hydrogen from water, which is quite available a lot on Earth. Yeah? So, but I will not be talking about the production of hydrogen, but I will be talking more about fuel cell. So, I will be talking about, firstly, on the R&D challenges in hydrogen and fuel cell technologies. What are the main challenges that we need to look at before we can actually commercialize fuel cell and hydrogen energy. And then we'll talk about the R&D focus in hydrogen and fuel cell technologies. What are the main problems that we face, and what are the solutions that we want to suggest. And then, of course, I will introduce to you the physical and electrochemical phenomena in various types of fuel cell. Mainly the proton exchange membrane fuel cell, as well as the direct methanol fuel cell and the microbial fuel cell. And then we'll look at some of the research fundamental as well as in trying to improve the performance of the fuel cell. In order to as well as to commercialize it. And I also talk about a little bit. Is it all right? Huh? All right. I will talk also on the hydrogen energy, hydrogen from water using solar energy. the photoelectrochemical cell as well as storage. So sorry. So what are the challenges in hydrogen and fuel cell energy? The first one is, of course, trying to produce hydrogen in a renewable way. At the moment, we produce hydrogen from petrochemical processes, from making your petrol and so on. You produce a lot of hydrogen, but it costs money because you need hydrocarbon in order to produce the hydrogen. But in future, when fossil fuel will be depleted, we might have to produce it in a more renewable way. And one of them is, of course, to produce it by using the photoelectrochemical cell, which splits water using solar energy. Yeah? So this is probably the holy grail of hydrogen energy. If we can break this this barrier, the efficiency barrier, then we will have hydrogen, you can produce hydrogen as much as you want by using free solar energy and water. Of course, the other one is, of course, the problem with fuel cell is, of course, the cost. So you need to be able to match cost of conventional energy technologies, and also to be able to use a variety of fuel, not only hydrogen, but also even the hydrocarbons, as well as even wastewater, which will look at a type of emerging fuel cell technology, the microbial fuel cell, where you can actually produce power directly from wastewater. The major barrier, as I told you, first is, of course, the cost, which is, we want to go down to $30 per kilowatt, which is not being achieved as yet. And then in terms of durability, we need to reach at least 5,000 hours. Yeah. So after 4 or 5 years, before you can actually replace the fuel cell. So what we have been doing is to try to reduce the cost and to increase the durability. And one way of doing this is to, of course, to use new nanostructures, nanomaterial, and nanosystem that can that are cheap and also can prevent some of the problem of degradation in the fuel cell technology. If you look at the cost of the fuel cell, the cost for a fuel cell system for transportation is reducing, as you can see on the left, going down to $51 per kilowatt of power in the fuel cell. And of course, the first large-scale introduction of fuel cell will be in the transportation sector because of the cost coming down. And you can see on the right the projected cost of fuel cell system for transportation according to the volume of production of the car, right? So in 2015, the first commercial fuel cell cars will be rolled out by the major automobile companies led by Toyota, Daimler-Benz, Honda, and so on, but probably not in Malaysia, but in countries like West Germany, where they have an extensive hydrogen infrastructure, as well as in California, Japan, and selected cities in Europe and the US. Now, what are the R&D focus in hydrogen energy and fuel cell? The first thing is, of course, the efficiency and stability of photoelectrode, especially the photoanode in photoelectrochemical cell. So some of the new direction are in using bimetallic organic dyes as the dye sensitizer for dye-sensitized photoelectrochemical cell, and also nanostructured metal oxide photoelectrodes Yeah? And the key is to try to improve the efficiency of harvesting the photon and to produce the electrical power, hydrogen, and increasing the efficiency, yeah? Because the efficiency is quite low, less than 5-6%. We want to target at least 12% of efficiency because you can commercialize the technology. And then a cost reduction of PMFC. Again, as I've said, we will use nano material, nano composite, as well as nanostructures for the electrocatalyst. And the durability problem as well, we want to prevent the catalyst layer degradation due to platinum dissolution and so on. So nanostructured material can reduce this phenomena. And then, of course, in the other type of fuel cell, direct methanol fuel cell, again, the focus is on the application of nano material, nanostructures in the electrolyte as well as in the electrode. And also in the microbial fuel cell, MFC, which is an emerging fuel cell technology where you can actually produce power from wastewater. This is just to show you how fuel cell work. You have in the middle the electrolyte, which is made up of the proton exchange membrane in the middle. And then on the side too, you have the cathode and the the cathode and the anode, and where you can have the hydrogen on the anode, yeah, split at the electrode. There's an electrochemical reaction here where the current is produced, the electron going to the outside circuit, and then the proton going through the electrolyte and then reacting with oxygen from the air on the other side and in the cathode, combining with the electron to produce water. So fuel cell produce only water. It doesn't produce any of the nasty stuff or carbon dioxide and so on, which is causing climate change. Yeah? In Malaysia, we don't have typhoons, but we have small-scale tornadoes occurring over the last few months, yeah? Which is unusual for Malaysia, right? So this is climate change, yeah, that you can see. Hopefully we won't have a mini tornado here in Taylor's University. And another type of fuel cell that is currently developed is the direct methanol fuel cell, where you, instead of using hydrogen, you can use methanol as a fuel. And in the past, we thought about having methanol supplied at the petrol station because it's liquid, it's easy to be transported to the service station. And in fact, Malaysia have the largest methanol plant in Labuan, yeah? Largest in the world, I was told. So if we want to straight away introduce methanol fuel in the petrol station, we can have a direct methanol fuel cell in the car and can use it for, yeah. And of course, methanol can be produced from renewable resources, for example, from biomass. And the more interesting fuel cell is, of course, the microbial fuel cell. You can see these are the microbes on the carbon paper anode that are used in the microbial fuel cell. And you can produce power from wastewater. So any kind of wastewater can be used, right? And you can see here the construction of the microbial cell. You have the dual chamber microbial fuel cell, and of course the single chamber microbial fuel cell. Now we are going to see people developing microbial fuel cell stacks. Yeah? And of course, there's some problem with the stacking the microbial fuel cell. It doesn't behave like a normal fuel cell, so we have to come up with some innovative way of stacking and producing more power from the microbial fuel cell. Now, what are the nanostructures and nanomaterial that we use in the membrane and electrode? And of course, you have seen this. This is single and multi-wall carbon nanotube, and this is the single-wall carbon nanotubes. This is a simulation, right? And this is actually the TEM image of the carbon nanotube, single nanotube. Yeah, and then this one is the multi-wall carbon nanotube, and you can see the walls, the many walls inside the carbon nanotube. And why do we choose carbon nanotube? Of course, it's not just carbon nanotube. We functionalize it with metal and so on to improve the catalytic property. Well, why do we use it? Because it has a unique geometric shape, very interesting shape, yeah, and it also have excellent mechanical strength, very strong, stronger than steel, and you can see here it's about 1,000 gigapascal. Yeah, the Young's modulus, and the tensile strength is about 60 gigapascal, very strong, and it has a very high electric conductivity. Yeah, 104 sievert per centimeter compared to carbon black. There's some missing figures at the end here. I think the presentation is shifted to the left, to the right. Well, it's larger than carbon black. And then, of course, because of the geometric shape, it has very large surface area compared to carbon black. And more importantly, for degradation and so on, it doesn't have micropores less than 2 nanometers, yeah? Which is present in carbon black, which tend to trap the platinum particle, and that would reduce the efficiency of the electrode, right? And it also has better chemical stability. It does not cause aggregation and dissociation of the platinum as you operate the fuel cell over time, because it does not corrode like carbon black. So it's very stable. It doesn't corrode. There's no there is no electrochemical reaction that will corrode the carbon itself, which can occur in carbon black. So CNT provide the, and then the other thing is, of course, the carbon nanofibers, and there are many types. Yeah, you have the herringbone, platelet, twisted spiral, ribbon-like, even tubular carbon nanofibers, and it also has similar properties to carbon nanotube. Yeah, and it's much stronger, and you can see that it has it has different shape to just simply carbon nanotube. Yeah, instead of just a tube, you can have herringbone, platelets, and so on, which offer some unique properties that you can exploit when you use it in fuel cell. And you can see this is the TEM images. You can see the shape, herringbone shape, and the platelet, as well as a spiral, and then the multi-ribbon-like shape of the nanofibers. And the latest one is, of course, graphene. Graphene is what we call carbon nanosheet, right? And this is an ideal representation of graphene, and this is actually a TEM image of graphene. And you can see the carbon, the 6-atom carbon shape in the image itself, right? In fact, from a sheet, you can produce a nanoshell or nanotube or just graphite. Yeah, graphite is a 3D, three-dimensional structure of carbon. So graphene also have similar properties with carbon nanotube. Yeah, it has high mechanical strength, high electric conductivity, large surface area, and better chemical stability. And these are the properties that we need when we want to apply it in fuel cell. Now, one way is, of course, to try to make the carbon nanostructure be more catalytic in nature, to be able to, for example, to do oxygen reduction reaction, yeah, which is on the cathode side of the fuel cell, where you have oxygen going in, and the reaction is called the oxygen reduction reaction. And you can see here one way is, of course, to replace some of the carbon with nitrogen. Yeah? So we have NCNTs, yeah? Which we've been doing in UKM. My doctoral student, Dr. Wong, she's probably present a paper later on in the symposium. And and this is the proposed reaction mechanism, yeah, that I took from Coleman, where you can see the oxygen coming in. Yeah? So, so the idea is, during the oxygen reduction reaction, there are two main paths. You can see one going to produce water, and the other to produce the hydrogen peroxide, yeah? Which we would like the reaction to go to water instead of to hydrogen peroxide. So a measure of the efficiency of the oxygen reduction reaction is, of course, on the how much of the electron being used to produce water instead of to produce hydrogen peroxide. So the number of, for example, for platinum, it's 4, for example, and we want to produce it at the different. Okay. This is another representation of the carbon nanotube and how we dope the nitrogen, yeah, in the structure, and we need the one which is having a paradinic structure. That's the one that is catalytically active, yeah, and this is the TM. TM of the CNT, yeah, you can see. So there are a lot of work on NCNTs, yeah, and Dr. Wong has been working on, producing NCNTs from various precursors, yeah, from aniline, from DA as well as EDA, and you will see the structure, the TM picture of it, right? These are all NCNTs that are made in our lab, and this is the property. You can see the number of electrons for the DA is larger than the rest, yeah, up to 3.6, from 3.1 to 3.6, and you can see also the paradinic structure. You have more of the paradinic structure in the EDA precursor producing the NCNT. And this is, of course, the voltammetry of the various type. We have here the DA and then the EDA, yeah, and not very clear, but perhaps Dr. Wang's paper will show a better picture. And this is, of course, the comparison with other workers, and you can see our result is not very far from the rest, and we hope to do more in making it. Yeah, right. Just so these are some of the structures that we made, carbon nanotube, yeah, for the MFC as well, and this is carbon nanofiber anode layer. This is quite recent paper. And then we also have multi-wall carbon nanotube anode layer, yeah, and so on. I'm told that I'm running out of time. So this we also applied in microbial fuel cell, yeah, catalyst dope on carbon nanotube. You can dope catalyst on the carbon nanotube, and you can see some of the performance of the fuel cell. Yeah, and then some other type of electrodes. Yeah, for microbial fuel cell. And this is the COD removal and the Coulombic efficiency. And as I said to you, the microbial fuel cell is used on wastewater, so it can also reduce the COD of wastewater as well as produce power. And some other electrodes, so many that I want to share with you, but there's not much time. We also apply nanomaterial in the membrane itself, yeah, in the membrane itself, where we can improve the membrane, the proton conductivity. Yeah, this is some of the work that was done in UKM, Dr. Mahreni's work, and some other nanostructure membrane applied in the direct methanol fuel cell, Prof. Siti Khartoum and Dr. Siam Huisan. And there are a lot the application by in microbial fuel cell, for example, the carbon nanofibers. This is the work of my former student, Dr. Gashemi, and there's a lot of it. And then, of course, the bimetallic dye that we made in UKM, right, for the photoelectrochemical cell, where we can split water by using solar energy to produce hydrogen. Not very much right now, but as we improve on the photoanode, we will actually make more. So I'll just pass through. This is the bimetallic dye that we made in UKM, yeah, and this titanium dioxide thin film that we put this dye on top of this titanium dioxide, and then this is the band gap and also the photocurrent produced by the cell. And we also work on metal oxide as well, and you can see here some of the structures that we use for producing photoelectrochemical cell. And apart from that, we also have used titanium dioxide coated nanofibers, yeah, to store hydrogen. So this is the storage capacity that we have, yeah, on the nanofibers that we work on. Thank you very much. Sorry.
It's okay. Thank you, Dr. Dato. And next, I'd like to invite our speaker, Professor Mushtaq, which you all met just a while ago. Just to let you know a bit about Professor Mushtaq, he's trained as a mechanical engineer, but he's very much, being the Dean of School of Engineering, very familiar with what we do as chemical engineer. Today he's going to address to us a topic on educating engineers in the Grand Challenge area. He's the best person to do this because if you look at his profile, he's pioneered a few things in education, among one of it being the first Grand Challenges Scholar program. He's also started a CDI engineering program, the first one in Malaysia. And also, he's the first to start off the massive open online course in Malaysia. So without further ado, I invite Professor Mushtaq.
Okay. Actually, after the first talk by, before this, when Chong wanted me to speak about something, he said, can you pick something related to chemical engineering? Now, some of you know I'm a mechanical engineer, although I actually love chemical engineers. I don't know why. I think because we share something. I share something with chemical engineers. We hate chemistry. You know, I was really shocked because every time we have a subject chemistry for engineers, I realize no one wants to teach it, and the students also don't like it. So I don't know why you become a chemical engineer if you hate chemistry, because otherwise I would have done chemical engineering myself. But anyway, it's too late now. So, he wanted me to talk about something, and he said try to link it to chemical engineering. But as a matter of fact, few of my postgraduate students are chemical engineers, and they will be sharing the work that we are working on
with you later. So I thought maybe I could speak about a more generic topic that's related to how to educate engineers in general. So, okay. Let me see what does this work?
So can you hear me? Yeah. Does it work now? What? Can you hear me at the back? Yes. A bit higher. Can you hear me now? Yeah. Okay, if you don't hear me, just let me know. Can I have the clicker? Oh, it's there. Okay, so let me start with a trivia. I think we work better when we are asked questions, and I was told that you guys like to answer questions. So let's say you are given these two options. If you are given these two options, option A, you get a $1 million right now. Not that I'm going to give you this, but hypothetically speaking, if the option is to get $1 million right now. Second option, I give you $1 today. Tomorrow, I double that $1. I make it 2. The day after that, I make it 4. The day after that, I make it 8, 16, 32, and so on. Which option will you pick? Okay. Those who will pick A, raise your hand, please. It's a trivial question. Okay. Okay. You keep your hands up, please. Keep your hands up. Okay. Those who don't want to pick A, please look at those guys who are picking A. Okay. You remember that you picked A, please. Okay. Now, why did you pick A? I think they don't trust me. They think I get the $1 million now, right? He won't pay us anything. Okay. Who will be picking B? Okay, so more people are picking B. Who will pick nothing? Because I don't think, who did not raise his or her hand yet? Oh, you did it. So, Prof, you know it's a trick, right? So that's why you don't fall for it. Now, one of the people who picked B. Okay, there, the lady there. Why did you pick D? You don't like the money. Yeah. Let me get you. Get a mic. Run. Yes.
I'm more glad to get money every day than one.
So actually, you rather get a little bit of money every
Yes,
day. Rather
yes.
you get all the 1 million, go and spend it in one day, and become poor again.
Yes.
Well, the way smarter of doing it. Someone wants to answer here. Please, so maybe shout. I think, yeah. So actually, he thinks that he'll get more than 1 million by the end of 30 days. Can you believe that? No. Okay, some people. I want everyone to get a calculator now, please. You have it on your mobile phone. Please just get the mobile. Let's play. I have only one slide. I'm just kidding. Yeah. Okay. Get your mobile phone out there and multiply 1 times 2 and keep on pressing equal, so that it'll keep on increasing and doubling it. So we start by 2, 4. Can you stay with me? 4, 8, 16, 32. Yes? You use the calculator, you will never be able to. Yeah. So okay. Let's repeat that. I'm going to count the 1, 2, 3, the days. Okay, so day 1 we have 2. Yes? You are not using the calculator, do you? Come and tell us. Yes. What's the answer? Give him. Yeah. Where's the? Is that? You turn it on. Okay. This is fun. Does it work? Never mind. Speak here.
So this is part of the geometric progression with the ratio of 12. So starting from 1, you will get 2, then 4, 8, 16, 32, 64, 128, 512, 1024, 2048, 4096, 8192, 16,384, 32,768, and so on.
Okay, so you have the answer. Okay, thank you very much. Isn't he great? He's doing chemical engineering, by the way. Yes, I'm serious. Thank you very much. Okay, so tell the answer. This thing doesn't work. No, let me do it. Okay, give us the answer.
Yes, I think the answer will be 2 to the power of 29, which is 536 million. Pardon me.
Yes.
About that, 537.
So you will get more than $500 million in 30 days. Can you believe this? This is actually crazy. As a matter of fact, I know this, and every time before I want to use this, I check it again, just in case the fact has changed. And I checked it last night, and it was $500 million. Now, what do we call this? Oops, what did I do? Sorry, can you put that back? What is this called? This is the exponential curve. You know, our brains are so wired to think linearly. Every day we get a little bit, and we move on. But there are so many things that are growing in this world exponentially. And guess what? Our brain is not designed to understand the exponential growth. No matter how, we need to actually train our brains to, I'm so sorry, I keep on pressing this. Go back? Yeah. Okay, have you heard of Moore's Law? So what does Moore's Law say? It says that the number of transistors that we can put into an integrated circuit is doubling every 2 years, then they say every 18 months, but there is a doubling impact. And this is actually changing the way we do things, changing our life, whether we like it or not. So in this century, I would like to call it not only the century of the grand challenges, but I would like to call it an exponential century. Reason why I would like to say this, because it has exponential challenges. The environmental challenges, the energy challenges that we are facing are not linear. They don't increase by 1 every day. They are somehow doubling in impact. But the opportunities that we have are also exponential. So I would like to talk a little bit about this. We have heard about the 14 grand challenges that the National Academy of Engineering has identified. They are in the area of food, so that's the nitrogen cycle. It's about energy, it's about water, it's about health, education, security, learning, the things that we are really in need of. And clearly, we are facing grand challenges. The reason why we say they are grand, because, okay, we had the solar technology with us for how long now? But still, it's not economical. We have fuel cells, but we don't know where to get the hydrogen for that, and so on, so forth. So if I take the Moore's Law example of exponential growth, as I told you, the number of transistors you can fit in is doubling. And that increases the speed of our computing, reduces the price of the computers, make, you know, the mobile phones that we have now have more computational power than the entire command and control center that put a man on the moon in the 60s, for example. And every one of us have it
now in their pocket. Now, this is repeating again and again in a number of areas. So when the Human Genome Project started, by the time 1% of the project was completed, the projection was for us to complete the Human Genome Project on the same rate, we will need 700 years. Because 1% took that long. But that projection did not take into account that the technology is moving in an exponential manner. And guess what? The project was completed in 7 years from then. Now, what is happening now? The price of the human genome sequencing and the genome sequencing in general is actually going down, that almost anyone now can afford to have that equipment in their lab to do it. So can you imagine, there are exponential challenges, but the opportunities that we have are also exponential. Why I have to tell you this? Because our brain is wired to pick on the challenges. If there's something difficult, we will know it. If we are having an issue or a challenge, we will know that, oh, I'm having this, problem. Let's say, I'm not supposed to say this word anyway. But if there is an opportunity, it's very difficult for us to see it. And the reason why I'm talking to you today, because we as educators, we need to develop a system in which we educate our students to understand the exponential growth in terms of exponential opportunities and exponential challenges as well. Have you heard of Innocentive? Innocentive. You haven't. So Innocentive is a very interesting company. It's an online company. Any one of you could just search it right now. Maybe after my talk. Don't do it now. And Innocentive is an interesting company that's taking innovation on an exponential curve. So what do they do? If you are a company or a government or a university or whoever, and you have a challenge that you have been struggling with, your scientists are unable to solve this challenge. You go to Innocentive, post your challenge, and post a reward. You say, if anyone can solve this, I'll give him or her $10,000, for example. And amazingly, people from all over the world have been solving challenges that NASA was struggling with, that mining companies are struggling with, that P&G is struggling with. And one of the examples that I really liked, and probably this is connected to this conference, P&G was trying to find ways to mix fluoride into the toothpaste. And because it comes in powder form, every time they try to mix it, it actually doesn't mix. And somehow their chemists were unable to solve this. They posted the challenge on Innocentive, and an electrical engineer solved it. And that person got a reward of $40,000 or so. So I'm personally registered there. I haven't made any money yet. But the interesting thing is they send me the newsletter that tells you what are the challenges that the big boys are struggling with. And I sometimes, think, wouldn't it be great if, like, my students solve this, then while they're educated, I make the money? Yeah, it's an idea. Okay, so opportunities are indeed exponential. Challenges are exponential as well. What's the name of the world's champion for chess? Garry Kasparov. Okay, you are wrong. So Garry Kasparov has lost to Deep Blue, which is a computer. Now, what does that tell you? Actually, computers now are getting better than humans at certain challenges. And this is, again, by the fact that our technology is, in certain aspects, is actually improving on an exponential curve. Now, I'll share a few quotes that it's meant to give hope, because every time we look at how stuck we are in terms of energy and water, you almost feel like you want to give up. You want to, stop your lifestyle, whatever you are doing. So the longevity revolution changes everything. 2/3 of all people who have ever lived past 65 are alive today. There is no trend more predictable today than the rise in older people. Think of the new economic opportunities: self-driving cars, smart windscreen, robots, health, vision, travel, leisure, education, you name it. Why I am telling you this? Okay, I'm from the School of Engineering at Taylor's, and I believe there are many educators around here. And we need to ask ourselves this question. Yes, while we are teaching our students fluid mechanics and chemistry and mathematics and everything, are we actually telling them what to get prepared for? Are we telling them that if you as an engineer want to make a positive impact, probably try to think of how to design things for the elderly, because this is a rising trend. And these people often do have some money, at least in the developed world. So how can we address that growing need? And for us to be aware of that, for us to be able to share that with our students, I believe it is very powerful. I have few more quotes. Manufacturing will continue to get cheaper. Can you imagine? Please read this very well. Almost any product will be about $1 per kg. Eventually, the cost of manufacturing, can you imagine buying your mobile phone per kilogram? Now, what does that tell you? We've got the manufacturing sort of worked out. And we will reach a stage, regardless of what goes into what you are manufacturing, it's around $1 per kilogram. So where will the money come from? The money will come from the design, the brand. And again, are we actually preparing our students to tell them, look, you as an engineer, you could think of how do you make the idea so interesting that you don't even need to worry about the manufacturing. Someone else has figured this out. With 3D printing, now we are talking about self-replicating machines. We can put, the technology exists now that we put a self-assembling, self-organizing colony on the moon. It's just not cost-effective yet. We can send machines that they will make more machines, and they'll make themselves, and they'll make robots and then probably they will send us raw material from the moon if we need that. But hopefully we don't. Superhuman. Now, I like this because I think our capability is also increasing. Now, some people say, oh, before I used to remember 50, phone numbers. Now I don't even remember my own number. But think about it. If my heart breaks down and I get a mechanical heart, and if my knee doesn't work and I get a mechanical knee, I don't think this is a bad thing. So I think what we are getting now, we are getting some thinking machines that are making us very smart. My brain, your brain, is actually now connected to the entire human knowledge that you could check whether this quote is right or I just cooked it up for you. You could check this right now. So isn't that great? So we need to view these things as positive kind of trends. So we have no choice but to do it. I have been teaching at Taylor's for 15 years now. I still remember the time where, yes, I'm that old, yes. The ladies, they say, yeah. So I still remember the time where, mobile phones has to be left outside the classroom. Then the mobile phone has to be off. Now, if you keep the mobile phone silent, we are very grateful, because it became part of part of you. If you forget your phone, you feel like naked, as this guy said. So these are trends. Now, if our future generations are connected, collaborative, what would we need to do? How are we supposed to educate our students so that they can be ready to benefit from all these exponential trends? Time is, okay, I'll just go very quickly. So what we've done in Taylor's, we call this holistic education. So we want to give the students academic excellence, we want to give them emotional intelligence, and also we want to give them entrepreneurial skills. So the way we do it, very quickly, you see, I think engineering has a PR issue. People don't think engineers are great, but 33% of the CEOs of the top 500 companies are engineers. We should be proud of that. Even without thinking of and being trained in the exponential kind of way of thinking. So imagine if education system re-examines itself or reinvents itself so that we purposefully put academic excellence, emotional intelligence, as well entrepreneurial skills in. I just jumped to, I have a test. Prof. Wahab has set for this, so he doesn't qualify to take it again. So very quickly, think of this. This is when, during World War II, planes, the Allies plane, go to bomb Germany. Then the Germans are trying to shoot down the planes. And the American army is thinking, we want to armor the plane. The plane. We want to put more armor around it. Now, as you know, armor makes the plane very heavy, more fuel. So we need to really optimize this in a way that we put the armor only at the place where it is needed the most. So what did they do? When the planes come back, they study them, how many bullets, how many bullet holes they have. So they divided the airplane into 4 sections. So you have maybe the engine section, the cockpit section, the body, and the tail. And they found that on average, the front, the engine will have 3 bullet holes, the cockpit will have 5, the body will have 1, and the tail will have 6. Question to you, which they went to ask engineers, the question is, if we have only 3 kilogram worth, let's say, of armor, which part of the plane I should reinforce? So who think that we should reinforce the engine? Raise your hand. Okay, one. Okay, who think that we should reinforce the cockpit? Raise your hand. Okay, you. Okay, who think that we should reinforce the body? Raise your hand. Okay, nobody. Who think that we should reinforce the tail? Okay, you. So who did not raise his or her hand? We need to reinforce the wing, which is there. Okay. So all of you are wrong. Okay, let me ask you a question. When the Germans attack the plane, statistically, this bullet will go all over the plane, right? Okay, so let me ask you a question. Where is the plane that had 2 bullet holes in the body? Where's that plane? It's in Germany. Yes? No, where is the plane that has 2? You know, statistically, if I shoot like that, statistically, the bullets will be distributed evenly on the plane. But I have, for the plane that come back, the plane that did not fall, they all have only 1. So the plane that had 2 or 3 or 4 bullets, where is it now? It falls down. So somehow the body probably had some very important part of a fuel tank, and we forget to fortify it. So we need to develop engineers who are able to think like that, to think in an exponential manner. I don't have time. I'll just jump right. So these are actually some of the projects that my students do. They build cars. They build solar boats. They build solar cars. They win races. They do great things. And, okay. So since I don't have time, my book is available for sales out there. Please buy your copy. Thank you very much.
interesting presentation, and at the end of the slide there is a book sold outside. Yeah, if you're interested, go ahead. We are limited in time right now, so if I can have one or two, or maybe three burning questions from the floor, one for each speaker probably. The first one to Professor Hidetoshi, second to Prof. Wan, who's coming back, and last one to Prof. Mushtaq. Any question for Prof. Hidetoshi? Yes.
Okay, my name is Don Dave. I'm a student from here studying Bachelor in Chemical Engineering honors. So for Professor Hidetoshi, when it comes to plasma equilibrium, why do we need heat? Okay. When it comes to plasma equilibrium, why do we need heat to achieve that plasma equilibrium state?
Why heat is needed to achieve the equilibrium state for plasma?
Yes, that's right.
I cannot catch the question. So anyway, you need the plasma is heat. Hmm?
Why?
Why?
You want to know why heat is required to achieve the equilibrium?
To achieve the equilibrium. Or is heat required to achieve the equilibrium?
Oh, no.
No, I think this is depend on the situation. So if for example, usually the plasma can be gets the energy from the electric field. At first, the electron gets the energy, right, from the electric field, and then the collision is frequently occurred in the atmospheric pressure because the electron, the density of the plasma is very high. So the energy exchange between the neutral species electron is so high. So the energy exchange is frequently occurred, and then so the temperature is relatively high from the electric field, and then almost the temperature is the same. So it means that almost this thermal plasma is almost the equilibrium state. So the energy from the electric fields.
All right, I hope the answer is sufficient. If not, then during the tea break, you can ask more questions. One more question to Prof. Wan. Anyone? Is it very clear regarding fuel cell? Okay, the last question to Prof. Mushtaq. No question. I guess everything was clear. Don't forget to buy his book later. Now I pass the mic to my co-chairman.
Right, thank you very much. We will now come to the end of the plenary session. Before we leave, we would like to appreciate our three speakers. So let me invite the chairman of SOMCHE, Dr. Chong, to come forward. For the first speaker, Professor Hidetoshi. Yep. To Professor Dato' Wan Ramli. And to Professor Mushtaq Al-Tabi. Yeah. Okay, before we move to our keynote speeches, what I'd like to, there's a little bit of a good news. There's a coffee break that the organizers have decided to have just outside here. So please proceed there first, and we will postpone the keynote speeches to start at 11:15 a.m. So there are two sessions, one at C604, the other session is at C606. So please choose wisely which one you want to attend. For now, we invite you for the coffee break. Oh, so C604 and C606, just to define it further, this is Block C on my left-hand side here. And if you take the lift up to 6th floor, it's C6 and room number 4404 and room number 6406. Thank you. For those who wish to collect your receipt for your payment, you will do so at the finance counter.